Okay, so I want to go on now and say something about episodic accretion, which we've already heard a little bit about from an observational perspective from Leonardo yesterday. And let's begin here with just a mention of the observations. So these are some light curves of young stellar objects from a review in PP6 by Mark. So what you've got here is time, and you've got a bunch of different objects shown with magnitudes there on the y-axis. And what you see here is that when you look at young stellar objects, rarely, but nonetheless sort of strikingly, there's a range of quite pronounced long timescale outbursts in those systems. And the object at the top here, V1057 Cygni, this curve here, you see this has an outburst that is maybe six magnitudes in brightness change taking place in that object. So in these systems, there's a range of phenomena. They may all be the same phenomena. They may be actually different phenomena that have similar observational manifestations. But these are all systems where it appears the accretion is extremely variable on a timescale that's much larger than the dynamical timescale of the inner disk, the rotation period of the star, or any of the other, if you like, natural timescales of the system. So as we've heard before, the most dramatic of these are the so-called FU-Orionis events after the prototype, and these are attributed to being disk accretion outbursts in which the accretion rate in the outburst phase can be perhaps as high as 10 to the minus 4 solar masses per year. So this is a factor of 1,000 or maybe 10,000 larger than typical accretion rates in young stellar objects. And these events maybe have durations of 10 years, up to 100 years. Perhaps some of them may have even longer durations, which would be rather hard to, of course, probe observationally. Now, as is also shown on this plot, there's a continuum of lesser outbursts. Sometimes some of these are called XOR events. And I would say, in general, the sort of full range of these outbursts is somewhat incompletely characterized for the observational reasons we heard about yesterday. So we observe this episodic accretion, and this raises a set of questions that are really both theoretical questions and observational questions. And the main one I want to focus on today is perhaps the most basic one. What is the origin of this episodic behavior? Okay. What disk processes or other processes can we trace it to? Perhaps this would actually tell us something, for example, about the nature of turbulence in disks, which was the sort of fundamental question we were posing this morning, if only we could understand really where these outbursts were coming from. But then, as we heard yesterday, in the context, for example, of thinking about early stellar evolution, there are potentially other interesting consequences to these outbursts. Is most of the stellar mass accreted during these brief outbursting phases, rather than the much sort of slower, continuous accretion that takes place over millions of years? So we heard yesterday, for example, those kind of events, dumping a lot of matter onto the star in a very short period, can even change the evolution of the star and potentially confuse us when we try to age date some of these young stars. So we'd like to understand whether that is really what is going on. Do outbursts continue throughout the disk lifetime, or are they only occurring during the very earliest phases? So as we'll see, most of the mechanisms that could produce these outbursts we think would be preferred at early times, but there's sort of an important difference, at least in principle, between them only happening early and them mostly happening early, but continuing at perhaps a lesser rate even into the later phases of young stellar evolution. And then finally, how do they impact planet formation? I don't think I'll really be saying anything about that today. That's really a fairly unexplored area of theoretical research. But certainly, if these outbursts continued into the epoch of planet formation, so maybe 1 million years or more than 1 million years after the disk was formed, then having the disk be much hotter and accreting much more vigorously, even for a short period of time, could potentially have some interesting impacts on things we care about. So I want to focus on this question of what is the origin of outbursts, and I shall warn you at the outset that there's not going to be a definitive answer to this question. We don't know what the origin of these outbursts are. So I'm just going to go through some various possibilities that have been advanced for where this is coming from. So there's basically, I would say, three main ideas for the origin of these outbursts. And the most popular probably, and the one I'll spend the most time on, not least perhaps because it's one I've worked on myself, is the idea that the accretion disk around these young stars is subject to a so-called limit cycle instability. So in this picture, the instability, the cause of the outburst, is really rooted directly in the properties of the disk relatively close to the star, maybe within about an astronomical unit away from the star. And the idea is basically that the disk there is fundamentally unstable to flipping between two states, a high accretion rate state, which is associated with the outbursts, and a much lower accretion rate state, which is associated with the normal quiescent phase of disk evolution. And we'll see how the physics of the disk might conspire to give us that kind of a situation. So that's one model. However, there are other models. One model, which has been looked at increasingly in recent years, is based on the idea that the outer disk may be unstable to producing clumps of material. So this may be this gravitational instability we heard a little bit about in the previous lecture, and we'll hear a little bit more about later in the week. So the basic idea here is that we might form clumps of material in the outer disk, which can migrate through the disk and suddenly dump a large amount of material into the inner disk on a short time scale. And that material would then be accreted directly onto the star. And then finally, there's actually a much older idea that what we're seeing, perhaps in some cases, might be very strong perturbations to the inner disk from binary stars on eccentric orbits, which would come into the inner region of the disk, and when they gravitationally interact with that material close to the star, would tend to funnel it onto the star. So I'll just maybe show one slide at the end from that kind of picture. But let's first of all discuss this accretion disk limit cycle. And I think the easiest way to motivate why we might be interested in this kind of model is by reference to a completely different kind of system which looks somewhat similar and where we think this is really what is going on. So what's shown here up on the top is the light curve of F Uranus from a review by Kenyon and Hartman. So here's time in years, here's the brightness of the system, and here we have this very sharp rise in the brightness, and then actually a very slow decline in this case, and the system still remains very bright 50 years after it's the origin of that outburst. Okay? So this is a young star, and the disk around the young star that's producing that outburst. Now on this lower panel, we have light curves from a very different kind of system. So this is the dwarf nova SS Cygni. So this is a white dwarf in a mass transfer binary system where mass is being transferred from the companion. It's forming an accretion disk around the white dwarf and being accreted onto the white dwarf. And the upper one of these panels is the actual observed light curve of this system. This is now time in days. This is about 2/3 of a year here. And what you see here is that this system has a low state, and then it has outbursts here which are about 4 magnitudes in the visual. And these outbursts, there's some short ones and there's some longer ones, but the sort of timescales of those outbursts are maybe weeks or months in duration. And the lower panels here are work by John Canizzo from 1993, showing models of these outbursts based on this accretion disk limit cycle instability I'm going to be describing. And if you just concentrate on this observed panel and this theory panel, you see here that these models, which were computed now more than 20 years ago, do a very nice job in matching those observations and giving us something that we see. So the basic story here is that these dwarf nova outbursts are modeled as a thermal instability, giving rise to a limit cycle in the disk. I'll describe what that means. And since we do a good job in reproducing these dwarf nova outbursts with that model, it seems sensible to think, well, maybe these F Uranus outbursts, which are sort of relatively similar in magnitude, they're much longer, but then, of course, the disks around young stars are much bigger than these dwarf nova disks, so you'd expect them to be longer. Maybe the same sort of thing is going on there. Okay, so let's, however, first, before we get to that, take a step back and just discuss, in general, the sort of two classical disk instabilities that are present. So we're going back now to thinking about alpha model disks, disks described by a viscosity that in some sense is something like a Navier-Stokes viscosity, and we're ignoring for the moment the details of really what is causing the turbulence and the angular momentum transport. So in the classical picture, we have this disk evolution equation we discussed previously. So equation for the evolution, the time evolution of the surface density, which is the diffusion equation depending on the kinematic viscosity nu. So this is a diffusive equation, but the solutions that you get to that will be unstable if the diffusion coefficient is such that the system is actually anti-diffusive rather than diffusive. Okay? And so the condition for that to happen is that if you consider the disk at some particular radius and calculate the equilibrium structure of the disk at that radius, assuming hydrostatic and thermal equilibrium, if you do that and you get a situation where when you take the differential of nu times sigma, that differential is less than 0, then you end up in a situation where a ring of material, or perhaps an annulus of material, doesn't spread out in the way we showed before, but instead tends to clump up into narrower and narrower rings separated by regions of vacuum. Okay? So that's described as a viscous instability. And if you sort of let that go, it would lead to clumping of the disk into rings. Now, if you just consider this in this sort of one-dimensional picture, where you've constrained the rotation rate to be Keplerian throughout the disk, and made the other approximations we made to derive that equation, then the origin of a viscous instability is normally taken to be an unphysical solution to the equations, right? Because in principle, it would lead to just everything clumping up into rings, and there would be nothing in the equations to specify what the spacing of those rings would be. Okay? So it's not really a very physical setup. In reality, of course, if you had a circumstance where the viscosity behaved in this particular way, something else would set in to limit that production of rings. For example, if the rings became too sharp, they would be unstable to additional hydrodynamic instabilities, which would tend to smear them out. And we'll discuss maybe what would happen in disks where you do produce rings tomorrow in the context of thinking maybe about how we could form vortices in rings. But anyway, this is a viscous instability. But then there's a second instability, which is related to an instability of the thermal structure of the disk. And to describe how this works, I first of all need to say something about the relationship between the midplane conditions in the disk and the surface conditions in the disk. So we can do that with a fairly simple analysis. Let's imagine we have a slab of the disk, so this would be the midplane, and this would be the height above the midplane. And we'll assume that the disk is being heated now by accretion rather than primarily by irradiation from the central star. And when we think about models for F-Uranus objects, that's often a reasonable assumption, because at these very high accretion rates that are produced during those outbursts, the heating by stellar irradiation will be much less important than it is in an ordinary disk, where the accretion rate is much lower. So if the disk is being heated by accretion, clearly there has to be a temperature gradient, if the disk is optically thick, between the midplane and the surface, in order for energy to be transported from the midplane to the surface and then eventually radiated from the photosphere. So the simplest model you could have is to imagine that all the energy was generated in a thin sheet at the equator of the disk, and then is just being transported through the disk vertically and radiated at the photosphere. And then we have two temperatures, a central temperature and an effective temperature, and we'd like to work out what the relationship is between those two temperatures. So to do that, let's assume that the energy is being transported by radiative diffusion. You could have a slightly different analysis if it was being transported by convection. And in that case, the radiative flux is just given by this vertical temperature gradient and this prefactor, which depends on the density, the Roslin mean opacity, and then we have this T-cubed factor coming in here. So the picture here is the energy is dissipated at the midplane, it's transported radiatively to the photosphere, and then it's radiated at this effective temperature TE. Okay, so you can take that equation, and because we've got no sources and sinks here, so the flux is just constant with height by the assumption that all the energy is coming out at z equals 0, we can actually directly integrate that equation and get a relationship between the central temperature and the effective temperature. And the relationship is very simple. The fourth power of the central temperature is the fourth power of the effective temperature multiplied by a factor, which is the optical depth between the surface and the midplane of the disk. So this tau here is the opacity times half of the surface density, reflecting that optical depth between the photosphere and the midplane. So this is actually a sort of important relationship for other things which we're interested in. If we ask where the snow line is, for example, if the disk is just a passive disk irradiated only by the central star, then it can be quite difficult to have the snow line out at 2.7 AU, which is where we infer it was in the solar system. So having some active accretion, which is heating the midplane with respect to the photosphere, is probably necessary if you want the snow line to be out where it's observed in the solar system. Okay, so we have that relationship. And then if we ask that the annulus of the disk is in thermal equilibrium, the rate of heating the disk material at that radius has to equal the rate at which the disk would be radiating that energy from the surface of the disk. So an expression we've used before, but which we haven't actually derived in these lectures, is that in a viscous disk, that heating is 9/4 nu sigma omega squared, where that's the heating now throughout the volume of the disk, both the upper half and the lower half. So in thermal equilibrium, that heating rate has to balance the cooling rate, which would be just 2 sigma, the effective temperature to the fourth, where the little sigma here is the Stefan Boltzmann constant. So we have heating has to balance cooling. The cooling depends on the effective temperature. The heating here depends on nu, and the viscosity depends on the central temperature in the disk, because the central part of the disk is where most of the mass is, and that where in this model, therefore, the turbulence would be generating the energy. So the viscosity depends on the central temperature. Nu is alpha Cs squared over omega, and the sound speed squared here is reflecting the central temperature conditions in the disk. Now, if we think about this a little bit, we can see that because of this relationship between the central temperature and the effective temperature, there is the possibility here that depending on how the opacity behaves, we might have a situation where we cannot reach a thermal equilibrium in the disk. And the way to think about that is if the opacity increases very strongly with temperature, if we perturb the temperature to some higher value, that will give us a higher opacity and therefore a higher optical depth to the midplane. Now, we still have to maintain in thermal equilibrium this relationship between the central temperature and the effective temperature. If we now increase tau, that implies effectively that the radiation has a harder job getting out through the disk because the opacity is higher, so the photons are having to scatter more times to diffuse to the surface. So increasing the central temperature leads to a higher optical depth. That leads to an even higher temperature in the midplane and correspondingly even stronger heating. So this can be a feedback loop here which doesn't come to a nice convergence. The interior of the disk gets hotter. As it becomes hotter, it makes it harder for the disk to cool because the opacity goes up. It can't cool, it gets hotter, it gets even hotter, and so on and so forth. So this kind of situation is described as a thermal instability in the disk. Now, more formally, you can ask when do you get that kind of runaway, and this would be the normal condition for it, if the logarithmic derivative of the heating rate with respect to the central temperature exceeds the logarithmic derivative of the cooling rate with respect to the temperature, you will get this thermal instability to take place. Now, physically, where this takes place is when the hydrogen becomes ionized and there's a very rapid rise in the opacity. So here's a standard simplified model for the opacity by Bell and Lin. So this is temperature, and this is the Rosslyn mean opacity. So down here we have low temperature opacities, ice and dust particles and so on. Here we would have gas phase opacities. And the point here is that at a temperature of about 10,000 Kelvin, you ionize hydrogen, and there's this enormous increase in the opacity due to that ionization. So you see here, probably the gas phase opacities here are underestimated in this Bell and Lin opacity, but nonetheless, you're getting many, many orders of magnitude of increase in opacity over a relatively short temperature range. So if you have a disk where these temperatures are attained, at least in the midplane, you have this rise in the opacity and you have the possibility of thermal instability in the flow. Okay, so here's then a sort of schematic of how it works. What thermal instability in a disk means, if we just focus on one radius of the disk where thermal instability takes place, is it means that there's a range of mass accretion rates which cannot be stably transported through the disk. And the way that's normally plotted is in a diagram like this, where you plot either the effective temperature of the disk or the mass accretion rate versus the surface density. And when you solve for the thermal equilibrium solutions of the disk, now at a particular radius, what you find is you get two branches. You get a lower branch where the gas is not ionized, and then you get a higher branch where the gas in the disk is ionized, where the hydrogen in the disk is ionized. And this low branch supports a rather low accretion rate through the disk, corresponding to a rather small effective temperature, and this upper branch corresponds to a much higher accretion rate and a much higher mass accretion rate, a much higher temperature. So this would be just for one radius in the disk. If many radii in the disk are subject to a similar instability, it's possible, though not guaranteed, that this will lead the whole disk to flip between quiescent and outburst states. So the general picture would be that when the disk is in quiescence, the annuli in the disk are living on this lower part of this S-curve in thermal equilibrium. The disk is rather thin. It has a rather low accretion rate. In the protostellar case, it's probably truncated by a magnetosphere at small scales, as we've already heard. And then at some point, it can flip into the outburst state, where the accretion rate is much higher, the disk is thicker, and probably the disk extends all the way down to the stellar photosphere. So you have a bistable situation where you flip between high accretion rates, ionized and outburst, low accretion rates, neutral, and quiescent. And the idea would be that the disk itself is trying to accrete at some sort of intermediate rate. So when it's in the outburst state, the mass is draining away. So it's trying to return to the quiescent state. But then when it's in the quiescent state, that's less accretion than it wants to do. And so the mass builds up. And so you get a cyclic behavior in this kind of diagram. Okay, so that's the picture of thermal instability that was developed, as I was saying, a long time ago for understanding the evolution of dwarf novae. Now, in many ways, this is quite successful. If you look at the disk conditions in protoplanetary disks, this was done by Robbins-Bell and Doug Lynn, now in 1994, and you plot these thermal equilibrium solutions, so these are now real calculations, surface density here versus central temperature. These are thermal equilibrium solutions constructed by vertically integrating the disk equations, taking appropriate account of the opacity and so on. You see that they do have this S-shaped morphology, which is characteristic of what you need for thermal instability. So the basic properties of protoplanetary disks do support the idea that they would be unstable thermally. Now, much more recently, so these calculations that Robbins-Bell did, and most of the early calculations, or all of the early calculations that were done for dwarf novae, were of course done using very simplified alpha model accretion disks. So they weren't explicitly looking at the turbulence within the disk. Now, much more recently, in work targeted purely at dwarf novae, Hirose and collaborators actually looked at whether you could produce one of these S-curves directly from MHD simulations, which include the magnetorotational instability and also radiation transport. And what's shown in this plot, the symbols here are the results of MHD simulations, is that MHD solutions also have these two branches, a lower quiescent branch and an upper outburst branch, that at least qualitatively behave the same way as one-dimensional models constructed using the alpha prescription. So it does appear that even though the original models were computed using rather simplified models of the turbulence, the same sort of physics really applies in actual MHD calculations. So that's all very good. However, in the protoplanetary disk case, this temperature that you need of about 10,000 Kelvin is really only reached, of course, at very small radii in the disk for quite high accretion rates. And that poses a problem, because if we look at these F-Uranus outbursts, some of them are going on for decades, maybe approaching a century in duration. And a very small disk has a very short viscous timescale, And so it's hard to see how the outburst could go on for so long. If you triggered one of these thermal instabilities in a protoplanetary disk, you would expect the region that was unstable to be rather small, and all of that material would drain onto the star on a rather shorter timescale, maybe several years, but not tens or hundreds of years. And indeed, to make these models work, these early calculations by Bell and Lin required alpha values that are maybe 10 to the minus 3 or 10 to the minus 4, even in the outburst phase of the eruption. Okay? And that's clearly inconsistent with what we expect from the magnetorotational instability, where we expect alpha instead to be more like 10 to the minus 2, consistent indeed with other observations of protoplanetary disks. It also implies extremely massive disks. If all of protoplanetary disks had alpha of 10 to the minus 4 and were able to support these very high accretion rates in FU Orionis events, that would mean that the disk mass would become self-gravitating, probably not far beyond the terrestrial planet-forming region, which would be a very unusual situation compared to what we think the conditions are in protoplanetary disks. So for these reasons, even though this thermal instability in dwarf novae remains the accepted explanation for what those instabilities are, it doesn't seem to be the whole story for what is going on in the protoplanetary disk case. So I think we'll stop at that point and take a 5-minute pause. And we'll then go on and say how we can modify this model a little bit, perhaps to make it more compatible with what we see in protoplanetary disks. Okay. So how can we do a similar thing? How can we perhaps maintain some of the successes of this sort of thermal instability picture, but adapt it better for protoplanetary disks? So the basic idea here is that what we would really like to do is, in some sense, independent of the details of the thermal instability part of the story. If we had a situation where, when we plotted equilibrium solutions to the disk structure in this plane of accretion rate versus surface density, if we have this S-shaped curve, which is what we obtain naturally from thermal instability, if we have this S-shaped curve for some other physical reason, the same sort of global evolution of the disk that gives us rise to quiescent periods and outburst periods can potentially still take place. So here's the idea here. We have this one radius, this S-shaped curve of consistent solutions of accretion rate versus surface density. Now, if we're in this middle patch, where if we increase the surface density, the accretion rate goes down, that's the unstable branch of this curve. So if we try to accrete in this unstable strip of the S-curve, then we have this local limit cycle. And so the picture would be that we're trying to accrete at this particular rate. Let's imagine we start on this lower branch. So we're trying to accrete, maybe this is 10 to the minus 6 solar masses per year. But we're on this lower branch, so the mass is only flowing through the disk, maybe at 10 to the minus 8 solar masses per year. So we're feeding this annulus of the disk with more matter than it's able to transport inwards. As a result, its surface density rises, and it tracks up on this S-curve until it reaches this corner here. At that point, it jumps to the high accretion rate state, where it now has a much higher accretion rate, maybe 10 to the minus 4 solar masses per year. And that accretion rate is now larger than the rate at which mass is arriving at the inner disk from further out. So the surface density then tends to drop. We track downwards on this upper branch until again we get to the corner, and then we drop back onto the low state. So in this situation, the disk never finds an equilibrium, a long-term equilibrium. Instead, it just circles around in this diagram, successively flipping between quiescent states and outburst states. So all we need is to find some physics which would provide this kind of diagram in this accretion rate surface density plot. Now, I'm skipping over here some considerable subtleties based on the fact that when you compute one of these diagrams, and when you see a computation of one of these diagrams, it's made at a particular radius in the disk. Now, to produce a global outburst of the disk, you need many annuli in the disk to cooperate with each other, to all flip simultaneously into outburst, and then flip back into quiescence. If that weren't the case, then the disk might be unstable, but it might just actually flicker in luminosity as individual radii go into outburst and quiescence. So there's quite a lot of subtlety there, which is really not fully understood at a fundamental level, as to really what are exactly the conditions for this local instability to give rise to global outbursts. So I'll just mention that as a complexity. I won't say more about what that involves. So how this might work in protoplanetary disks could be related to the sort of dead zone physics we were talking about this morning. So this has been called the Gravo-magneto instabilities. This is Rebecca Martin and Steve Lubo's name for this kind of picture. And the idea here is that the lower and upper branches are not directly any more related to the ionization of hydrogen. Rather, the lower branch is one of these dead zones at small radii in the disk where ohmic diffusion strongly damps the magnetorotational instability, giving you a very low alpha and a disk that is unable to transport material inwards very efficiently. So this lower branch is an ohmic dead zone, and that therefore is unable to transport gas flowing in from outside if the gas flowing in from outside exceeds the maximum carrying capacity that dead zone can have. So if you start then on this lower branch, the same thing happens. The surface density will rise until eventually you have a very dense disk, maybe at 1 AU scales away from the star. And the idea simply is that if you have enough surface density at 1 AU, then in the quiescent state, the disk is very dead. Only The ohmic diffusion is damping things very, very strongly because you now have an enormous column to the sources of ionizing radiation. But if you could somehow heat that material up so that it was the alkali metals were ionized, then because the surface density is so high, it could actually sustain itself in the thermally ionized MRI state with a much more vigorous level of turbulence corresponding almost to ideal MHD. Okay? So at the same surface density, which would be a high surface density, there's this lower state where the disk has a dead zone and the ohmic diffusion is damping turbulence, but then there's a high state where that same column of material is very vigorously turbulent and the alkali metals are ionized and enough heat is being produced to keep them ionized with time. Okay? So in this picture, you go up on this lower branch, something here happens to heat the disk up, and the picture here is that the disk becomes massive enough for self-gravity to take place, even at these relatively small scales. You jump up to this upper branch where you have the active MRI, you then have a very high accretion rate, higher than the disk is being supplied from outside, so the surface density then falls, and you have this limit cycle taking place once more. Okay, so that's the cartoon picture of it. Here's some calculations by Rebecca Martin and Steve Lubo. So here again, you've got surface density. Here you've got mass accretion rate, shown on this right-hand axis, and effective temperature, shown on this left-hand axis. So here on the bottom, you have calculations of dead zones, here at 3 AU from the central star. And these different dead zones have different assumed levels of residual turbulence taking place in that dead zone region. So the dead zone may not be completely dead. Probably there's some waves stirred up in the dead zone from outside, which enable it to transport at least a little bit of material in. And here you have alphas of 10 to the minus 5, 10 to the minus 4, 10 to the minus 3. At the top here, you have this branch where the alkali metals are ionized, and you have near-ideal conditions for the MRI. And what they find here is that there is indeed an unstable strip in this diagram, and a region where if the disk was being fed at this accretion rate, you would have to be either in the low state or in the high state, and you'd have this kind of limit cycle behavior. So what seems to be quite attractive about this is that if you think about what the T-Tauri accretion rate might be, that might be 10 to the minus 7 or a little bit less than that solar masses per year. So that would fall on this lower branch of the curve. If you then jump, say, from this dead zone alpha of 10 to the minus 4 curve directly up onto this high state curve, then you're up at an accretion rate of 10 to the minus 4 solar masses per year, and that's more like the F Uranus kind of accretion rate. And here, we've tied the outburst not to the ionization of hydrogen, but here we've tied it to the ionization of potassium and sodium, which is happening at a factor 10 lower temperature than the ionization of hydrogen. So instead of a very small region of the disk being unstable in this way, the region that's unstable is much larger, and therefore the viscous time when the instability is triggered can be much longer because your R squared over nu, R squared now is much larger when we're going out to 1,000 Kelvin temperatures than when we're going out to 10,000 Kelvin temperatures, as we would need for a classical thermal instability. Here's another picture asking how this works at different radii. So here's accretion rate, and here's radius here. This white part of the diagram marked as unstable is that region where you can't find solutions that are not either on the low branch, the dead zone branch, or on the thermally ionized ideal MHD branch. And the point here simply is that over a range of radii, you have this unstable strip, and that means that there is the possibility of this local instability, if you like, connecting together to produce global outbursts of the disk. So this, in some sense, is quite attractive for the reasons I was mentioning. The disk is unstable for broadly the right accretion rates if you want to produce outbursts, and then because you have this lower critical temperature, you trigger the outburst further out, and when it happens, it lasts much longer than it would if it was really a true thermal instability. Okay, so that was some work from Rebecca Martin. Here's some work from some other people. So this is work from Zhao Zhu and Bayan collaborators. And so here's an example of what one of these outbursts might look like. So here you have a low accretion rate state at a few 10 to the minus 7 solar masses per year. Here a very high accretion rate state, even approaching several 10 to the minus 4 solar masses per year. And here an outburst duration maybe of a couple of hundred years. Here on the right is a calculation showing the burst length and how that depends on various parameters, on the infall rate at which the inner disk is being fed from outside, and then parameters describing how efficiently energy is being transported radially in the disk. And then on the bottom here, rather different kinds of calculations. So these kind of calculations were purely one-dimensional disk calculations. Here on the bottom is a more recent calculation done with a two-dimensional model of the disk that explicitly tracks the onset of self-gravity. And here, for different assumptions about how dead the dead zone is, there are plots showing what fraction of the time you would be in the quiescent phase, you would be in the outburst phase, or alternatively would have some sort of quasi-steady accretion at an intermediate accretion rate. So these calculations show that maybe 5 or 10 or 15% of the time you'd be in the outburst accretion rate state. The majority of the time, instead, you would be in the quiescent state. Okay, so those are all well and good. So in that sense, the calculations that have been done to date are fairly plausible as a way of producing these F-Uranus outbursts. But as I was saying at the start, I wouldn't like to claim that this really is what's going on in these systems, because there are important pieces of physics that have not really been considered at all in constructing these kind of models. And the most important of those is the one we mentioned this morning, which is that if you just do simple estimates of how important the different non-ideal effects are, in the inner disk, ambipolar diffusion is negligible because the density is high, but the Hall effect is generally estimated to be an even stronger non-ideal effect than ohmic diffusion. And the calculations I showed by Geoffroy-Lesure and collaborators this morning of disks at 1 AU and a few AU with the Hall effect showed the development of this very strong laminar stress that wasn't actually described by turbulence at all. Okay? Now, it may be that if you redo those calculations, including the effect of the Hall effect, you may also find that the disk on those scales is unstable to these kind of S-curve instabilities of the kind we've been discussing. But no one has done those calculations, and actually even the simulations of the Hall effect at the moment are still at quite a preliminary state. So there's substantial uncertainty there about whether the pieces of physics that have gone into those F-Uranus models, whether really a critical element is missing. So that's something perhaps that hopefully will be possible from a numerical point of view within the next few years. And then there's a more observational point, which is that when you do those calculations, so if you look here at these calculations of Zhao, and these are ones that James Owen did, these burst durations you get are typically F-Uranus type durations, and in some cases even longer than F-Uranus type durations. So in some sense, you've solved that problem of wanting the outburst to be long that was present for the thermal instability, but maybe you've oversolved the problem. The outbursts, if anything, are getting to be a little bit too long compared to what you'd like observationally. And in particular, we know that there are lesser outbursts. That observational plot I showed at the start had outbursts that were of shorter duration and lesser magnitude, and it's really not so easy to see how those fit into these kind of disk instability pictures. So maybe those lesser outbursts are just a different mechanism and it sort of looks somewhat similar observationally, or maybe they're all the same kind of outburst and that's saying there's something wrong with this kind of picture. Okay? So let me now mention then the alternatives to this disk instability idea. So the most popular alternate model is one based on clump tidal disruption. And the idea here is that somehow you feed the inner disk with material at a rate that's much larger than the normal viscous rate at which material can be transported from the outer disk to the inner disk. And the way this normally is thought to work is a situation where the outer disk, maybe on scales of 10 AU out to 100 AU, is gravitationally unstable and breaks up into clumps of material. Okay? So maybe those clumps have masses of a Jupiter mass or a few Jupiter masses. Now, some models, those clumps contract to form giant planets, and that's a potential way of forming giant planets a very large distance from the star. However, if those clumps collapse or contract at a time when the disk is still very young and massive, the clumps themselves may interact gravitationally with the disk very strongly. Okay? So the clumps that form may migrate radially. This is a process that we'll, I think, hear about more tomorrow, called type 1 migration. And type 1 migration can be extremely fast. In particular, it can be much faster than the viscous timescale of the disk, and conceivably it could even be faster than the timescale on which those clumps would themselves contract by losing thermal energy. So if they migrate very rapidly inwards while remaining quite large and fluffy, when they get to small radii, they might be tidally disrupted by the tidal gravitational field of the central star. And that will happen when their density is smaller than something like the stellar mass divided by r cubed. And in that case, the outburst is this material which is being tidally disrupted. It's being fed directly to the disk on a very small scale, maybe less than a tenth of an AU, and it just piles directly onto the star. And it might, in the process, trigger thermal instability or trigger the ionization of hydrogen, so it would look very much like the previous model, but the actual origin of it is completely different. It's got nothing to do with an instability of the accretion disk. It's material that's being fed from outside. So Vorobyev is the person who's done the most kind of work on this kind of clump formation in the outer disk. Sergei Nyakshin and Lodato, Aaron Bowley and collaborators have also looked at models that are broadly in this class. Okay, so here's an example. This is work, I think, here from Vorobyev and Bazou. So here's a two-dimensional simulation of a disk, very gravitationally unstable. Here you're looking at 100 AU scales in the disk. You're forming these clumps in the disk due to gravitational instability. And then here is the mass accretion rate through some inner radius of the disk. Unfortunately, not the stellar radius, but some much larger fiducial radius in the disk. And so here you can see these spikes here. This is now a very long time scale here, about 0.5 of a mega year. And these individual spikes in this model would be F-Uranus type events. Now you can do some estimates to see whether this is kind of a sensible model. If you imagine that the inner disk has h over r of 0.1 in this high accretion rate state, and alpha of 0.1, this would be the expression for the viscous timescale we gave before. So that time is about 10 years at a radius of about 0.05 of an AU. So if you want to make an outburst this way that's going to last 10 years, you would want to be triggering it by this clump being disrupted at about 1/10 of an AU or a little bit smaller than that in the disk. Now, if you ask, would a Jupiter mass clump be tidally disrupted at that radius, the condition you would need for that to be true would be that the density is about 10⁻², grams per cubic centimeter, so much lower than, of course, the actual density of Jupiter. And so this would correspond to this Jupiter mass clump having a radius of somewhere between 5 and 10 Jupiter radii. So this would work if you could form one of these clumps in the outer disk, move it to this very inner region close to the star, while the clump was still large enough, then it would be tidally disrupted, it would dump the material onto the inner disk, and you would get something looking like an F-Uranus event. Okay, here's another calculation, Nyakshin and Lodato, who looked actually at how this disruption would take place. This is accretion rate now as a function of time, some complicated structure reflecting the fact that what's happening here is basically Roche lobe overflow of this disrupting clump, which is giving up its material to the disk and then changing its orbit as a result of that loss of mass and angular momentum. So the key questions for this kind of model, from an observational point of view, is clearly this only works if the disk is very massive, so that the outer parts really are gravitationally unstable and are currently forming clumps. So an observational question is simply, are all the objects where outbursts are being observed systems where the outer disk is massive enough that they could plausibly be gravitationally unstable? Now, the theoretical questions, on the other hand, are sort of twofold. One is whether the clumps migrate fast enough. Most of the calculations that have been done to date that really explicitly track the evolution of the disk don't go anywhere near close enough to the star to really see whether they go all the way to being tidally disrupted. And then maybe more critically, do they remain large enough during that migration process? So as we may hear more about, trying to estimate how quickly a giant planet contracts, how quickly it loses energy thermally and therefore contracts to smaller scales, is rather a difficult question because it depends very much on what the opacity in the envelope is like. So different groups who've tried to model this come up with different numbers, but differing maybe by as much as an order of magnitude. You really want the clump contraction to be very slow, basically as slow as it could be, if you want to have as much chance as possible for those clumps to get in close, be tidally disrupted, and give you the F-Uranus phenomena. Okay, so then let me finish then with just one slide on binaries. So this is a much older idea dating back to work by Ian Burnell and Bastian, now from the early 90s. And the picture here is simply that you have a disk that's now in a binary system, and the binary companion, which might potentially be a low-mass companion, has a very eccentric orbit, which brings it, roughly speaking, into the terrestrial planet region of the system. And if you do that, what will happen is that each time the binary comes in on one of its periastron passages, it will plow through the disk and will tend to push some of that inner disk material inwards, where potentially, again, it could trigger the onset of hydrogen ionization, perhaps, and a thermal instability in the disk. So these are some simulations by Duncan Forgan and Ken Rice. Here's a picture of the disk, again on about the same kind of scales. And now maybe you can see here's the companion. It's coming in, it's very strongly disturbing the disk as the companion comes in. And then if you plot the accretion rate onto the stars as a function of time, you can get these bursts taking place. So here's the first periastron passage, get a very strong burst, up to maybe 10 to the minus 4 solar masses per year. By the time you've done that, you've sort of partly destroyed some of the disk. So the next time the binary comes around, you get a smaller burst. Later, you get a smaller burst, and so on. Okay? Now, these calculations are just sort of the raw accretion rate from the simulation. They don't take account of the fact that the disk might respond thermally in some complicated way to having its surface density increased very much on small scales. So, these are not direct calculations of the light curve you would expect in an F-Uranus event. Nonetheless, clearly the prediction here is quite obviously that both the primary and the secondary should accrete very vigorously as they come to closest points of approach. And that's the main sort of issue with this model. Why don't you see these binaries in these F-Uranus events? Now, of course, there's a lot of material in many of these events. They're very deeply enshrouded, so maybe you can hide a low-mass companion. But here we would be predicting that even a low-mass companion, perhaps, would be accreting very vigorously as a result of the perturbation of its own accretion disk when it gets close to the primary. But nonetheless, there ought to be such binaries, and if there are such binaries, we would expect that this dynamics would give rise to some kind of transient outbursting behavior in those systems. So I think I will stop there and take some questions. Yeah, so the question was whether in these dead zone instability models you'd expect the instabilities to continue to late times when they're not generally observed. And I think that's a correct summary of the situation, right? In those models, what you would expect is that the instability should still be present, but it should just become much rarer because as the disk evolves, it takes much longer to accumulate the unstable conditions in the inner part. But in principle, there's no reason, indeed, why it shouldn't happen. It shouldn't happen late. And so the expectation here, yes, would be that very rarely there ought to be such instabilities taking place, not in almost the embedded phase, but at some much later evolutionary phase. So that is a prediction of that model. Yeah, so if it's 10 to the minus 8, and you say maybe that each outburst involves 1/100th of a solar mass, 10 to the minus 4 solar masses for 100 years, then yeah, 10 to the minus 8 accretion rate from the outside, you'd say once every million years would be the sort of estimate you'd come up with, yeah. Yeah, so the question was, in that work by Bai, the outburst phase was maybe 10% or 15%. The other phases were 85%. That's probably not an extreme enough ratio compared to what we observationally see. And I think that's reflecting the fact that the outbursts that are produced in these models tend to be longer than the actual outbursts that are observed, right? And it's, I would say, not clear to me whether that reflects, just something you could change about the models, something we don't quite understand about the physics that would bring them into better agreement there, or whether it says instead, that's really a fundamental problem and you're producing outbursts that are always too long and have too long a duty cycle compared to what's seen observationally.
One more question.
If I ask you to pick one of these three labels, which one would you pick?
I will pick the disk instability picture. But not necessarily for good reasons that you should believe, right? It's just it's one I've worked on, so I have extra emotional attachment to that, So. Well, I think the other question about the binary one is, as you can see from this plot, each passage of the binary does a lot of damage to the disk. So generally, when we think about disks in binaries, we imagine that the size of the disk is smaller than the periastron distance of the binary, maybe a third of the periastron distance of the binary. So the circumstance where you can have a really large disk and another star plowing through it is a situation you can't keep up for very long. So I would imagine that this process must happen, but probably this really happens in the very early phases, right? When really you're in the protostellar phase. So maybe it's associated with, some episodic jets or something like that. So there might be some, lots of interesting things, but the idea that it's really associated with optically visible outbursts is I think, a little bit harder to understand.
One last question. I know you're all anxious to go curling, so we have to cut this short.
Yeah, in the disk instability scenario, these clumps were also star, but how do we explain this balance of how could they be formed by
Yeah, so I would say these models for F-Uranus events, the idea is that basically gravitational instability in the outer part doesn't generally produce massive planets. Perhaps you could have a situation where if the disk instability happens early and there's really a lot of mass in the disk, you get this rapid migration. If it happened later, then the clumps wouldn't migrate. They would contract basically in place on the outer disk and give you giant planets. But it is basically a different picture for what happens after disk instability than the classic idea that makes giant planets or brown dwarfs.